Assalamu alaikum to you all. In this lecture, we shall be talking about NP-Completeness. And this is the outline. First, we gave a small introduction about the topic. What is NP-Completeness and why do we need to study about it as computer scientists? Then we differentiate between optimization problems and decision problems, because actually NP-completeness applies to problems that are called decision problems. And most of the problems we have studied so far, they are optimization problems. Although actually you can usually cast an optimization problem as a decision problem. Then we differentiate between tractable and intractable problems. When do we say a problem is tractable and when is it not tractable? Okay, then we classify problems according to their tractability. And we're going to study 4 categories. First, we have a class that is called P, a class of problem that is called NP, and a class of problems that is called NP-complete, which, as you saw there, is the title of our lecture. So we're going to spend a lot of time explaining what this class is. There's also another class called NP-hard. Yeah, so these are the 4 main classes that you can classify problems according to their tractability or difficulty in solving. Finally, we take a number of examples of problems that are NP-complete. Okay, so this is the outline of the lecture. So we start with an introduction. Now, so far, we have seen a lot of good news. Okay, we have seen that such and such problem can be solved efficiently. That is close to linear time, or at least that is some small polynomial function of the input size. Okay, n to power k, big O of n to power k, where k is usually a small constant. So all the problems we have seen so far in this course, such as the rod cutting problem, the matrix chain problem, various sorting algorithms, and so on. Even the problems that we saw in the data structures course, like the shortest path, we always at the end come out to say the efficiency is some polynomial time. Okay, usually big O of n to power k, where k is some constant. Now, NP-completeness, on the other hand, is a kind of bad news. Okay, it is an evidence that many important problems cannot be solved efficiently. Unfortunately, NP-complete problems come up very often, and as a CS student or as a computer scientist, you need to be aware of those problems that are NP-complete and be able to recognize them when you encounter them. Why is that? Meaning, why do you need to know if a problem is NP-complete? Well, knowing that a problem is hard let you stop wasting your time trying to find an efficient algorithm to solve it. Instead, you could follow one of the following measures. Use a heuristic that has come up with a method for solving a reasonable fraction of the common cases. You cannot solve it as a whole using an efficient algorithm. So look at the common cases and come up with a heuristic that can be used to solve them. Another option, as we shall see in the next lecture, which will be our final lecture inshallah, is try to approximately solve the problem. In other words, come up with an approximate solution. Okay, solution that you can prove is close to optimal. Okay, so if you cannot solve the problem because it's going to be intractable, you can approximate, in some cases, the solution. Okay, and for some problem you cannot even come up with an approximation. So in that case, you have no option but to use the exponential time solution. If you really have to solve that problem, that is the only way out. You may not, of course, solve it wholly, but at least to certain number of size of the input, you may be able to solve it, even though you have to use the brute force approach. All right. But the main thing is, as a computer scientist, you need to be able to recognize these problems, okay, and know that this problem is there is no efficient solution for it. Right. Okay, so let's differentiate between optimization and decision problems. NP-Completeness applies specifically to decision problems. So what are decision problems? Problems that, given an input and a question regarding a problem, we can determine if the answer is yes or no. Okay, so decision problems simply at the end tell us only yes or no. Okay, on the other hand, optimization problems, as we have seen, for example, in dynamic programming and also in greedy approach, these are problems where you are to find the optimal solution or best solution. Minimum if you are trying to minimize the cost, or maximum if you are trying to maximize the profit. Okay, so in optimization, we are trying to find the best solution. However, optimization problems can usually be cast as decision problems. To give you an example, the shortest path problem for a graph G, which is unweighted and directed, could be find a path from U to V that uses the fewest edges. Okay, so fewest edges, we are trying to minimize the number of edges, so it's an optimization problem. How can we cast this as a decision problem? Like this. We can say, does a path exist from U to V consisting of at most k edges? Of course, the answer to this question will be yes or no. Okay, so you will try to find the shortest path, count the edges that you get, and see whether it is not more than k. Yeah, so although as we shall see, NP problems are mainly decision problems, even optimization problem actually can be cast in a way that we can try to see which class of NP does it belong to. Right. Okay, now let's talk about tractable and intractable problems. Problems that can be solved in polynomial time are called tractable problems. A polynomial time means the running time is going to be in form of big O of n to power k for some constant k. Hopefully the k will be small. Okay, if you can do that, then the problem is said to be tractable. Problems that cannot be solved in polynomial time are called intractable problem. or simply unsolvable. All right, that is, they can be solved in reasonable time only for small input sizes, or cannot be solved at all. All right, theoretically or technically, this is the difference between the two. One group are called tractable because they can be solved in polynomial time with respect to the input size, whereas the other group, the running time is going to be not polynomial, okay, like exponential or factorial or something like that. Okay, but non-polynomial algorithms always worse than polynomial algorithms. Here one has to be careful. For example, if the running time of an algorithm is n to power 1 million, yes, 1 million is constant. However, 1 million, of course, is constant. So technically, we will say that this is polynomial and therefore is tractable. Okay, so technically it's tractable. But clearly, to power 1 million is an impossible number. So even though technically it is polynomial, in reality it is actually impossible to solve. On the other hand, if you have an algorithm whose running time is n to power log of log of log of n, okay, technically the exponent here is in terms of n, so it's not polynomial. All right, and therefore it is intractable. But because log is a very slow growing function, and not only that, we are taking the log of that and then the log of that, this value is going to be very small number, even for very large input. Okay, so this problem, even though it looks exponential, it is actually easy to solve. Okay, so we should bear this in mind when looking at the running time of algorithms. We shouldn't just concentrate on the technical aspect. Yes, it is technically easy if it is a constant power of n in terms of running time, but that constant power could actually be a very large number, and the reverse is also the case. Okay, let's give some example of unsolvable problems. Alan Turing discovered in the 1930s that there are problems that can be described as unsolvable by any algorithm. And the famous of those problems is the Turing's own halting problem. Okay, what is the halting problem? It says, given an arbitrary algorithm and its input, will that algorithm eventually halt? In other words, will it terminate? Or will it continue forever in an infinite loop? Given any algorithm, can we come up with another algorithm that will tell us that this algorithm will terminate? Unfortunately, this problem cannot be solved. Okay, so this is an example of unsolvable problems. This is another one that is probably more clearer. Hamiltonian cycle. Okay, as an optimization problem, we can cast this as the following. Given a graph, find a cycle that passes through every vertex exactly one time. Okay, so given a graph, find a cycle that passes through every vertex exactly once. Now we can cast this as a decision problem by saying, does a given graph like the one we see here, does it have a Hamiltonian cycle or not? Okay. Unfortunately, there is no algorithm so far that can tell you that. Although if you are given a solution, you can easily test whether the solution is actually correct. The edges here shaded in red clearly shows a solution because we have a cycle that goes through all the vertices of the graph. But finding an algorithm that can give us this cycle, so far nobody has been able to come up with an efficient one that its running time is polynomial. Okay. Another example is traveling salesman problem. Traveling salesman problem, as an optimization problem, we can cast this as follows. Find a minimum weight Hamiltonian cycle. So it's very similar to Hamiltonian. The only difference is the edges, they have weights. And we want a cycle that goes through all the vertices, but with minimum cost. Okay. Yeah. As a decision problem, we can cast this as, is there a Hamiltonian cycle with a total weight of at most k? Okay. So go through all these edges and see if you can find a cycle whose total cost is at most k. This problem, again, so far, no efficient solution has been found. So it's an example of intractable problems. Okay, so this gives you an idea of tractable and untractable problems. Let us now turn to our classification of problems in terms of their tractability, or how difficult they are in terms of coming up with an efficient algorithm to solve them. Okay, so technically the following terms are used to classify problems based on their degree of difficulty. P, NP, NP-Complete, and NP-Hard. Okay, we're going to take each of these terms one by one and explain what it is. Of course, the ordering here is in the order of difficulty. So P are the easiest, then NP, then NP-Complete, and then NP-Hard. Let's start with the P. The P actually are the good news. Okay, P consists of a class of decision problems that have polynomial time deterministic algorithms. Okay, that is, they are solvable in big O of n to power k. Okay, where k is constant. So the big O is polynomial time. Now here we mention deterministic algorithm. A deterministic algorithm is essentially one that always computes the correct answer. Okay, so you have a deterministic algorithm, and if you evaluate running time, it will be big O of n to power k for some constant k. In that case, your problem is classified as P. Okay, P here stands for polynomial time. All right. Obviously, all the examples we have seen so far in this course and also in the data structures course, they can be categorized as falling into this category. Okay, so these are examples of big O's that can be considered as polynomial. If you have an algorithm that is big O of n squared, n cubed, big O of 1, n log n, n to the power 4, and so on. These are all polynomials, and therefore such algorithm will be considered to belong to class P. Okay, as I said, most of the examples we have seen so far in this course belong to class P. So what are examples of non-polynomial time, which are also called super polynomial time? If your algorithm turn out to have a runtime of big O of 2 to the power n, so it's exponential, or was n to the power n, or n factorial. Okay, n factorial is almost like n to the power n, because n times n minus 1 times n minus 2 and so on. So if an algorithm turn out to have one of these, then it is said to be a super polynomial. It doesn't belong to the class P. Okay, good. Okay, let's now turn our attention to non-deterministic and NP algorithms. Non-deterministic algorithms involve two stages. Okay, one is the non-deterministic part, which involves guessing a solution. So there is no a deterministic algorithm that can give us a solution. But somehow, either by trial and error or by guessing, okay, or by some magic, you may come up with a solution. Okay, so there is no deterministic algorithm to find a solution, but somehow a solution may be found. Okay, so this is stage number one. Generate randomly an arbitrary string that can be thought of as a candidate solution. Technically, this is called a certificate. So a certificate is like a candidate solution to your problem. Now the second stage is deterministic verification stage. Okay, in other words, if you take the solution that you are given to you, which was generated non-deterministically, it will take, there is a deterministic algorithm that can tell us whether that solution is correct or not. Okay, so take the certificate and the instance of the problem and return yes if the certificate represents a valid solution and no otherwise. Okay, now NP algorithms, also called non-deterministic polynomial, are those that satisfy these two conditions. So the algorithm itself is non-deterministic, but verifying a candidate solution can be done in polynomial time. Okay, if an algorithm satisfies these two, then it is said to be NP. Let me give that in more formal way. So the class NP consists of problems that can be solved by NP algorithms. Okay, algorithms that their solution cannot be generated in a deterministic way, but if a solution is found, it can be verified in polynomial time. Okay, if we are given a certificate of a solution, we could verify that the certificate is correct in polynomial time relative to the size of the input. If that is the case, then the problem is said to belong to NP. Okay, there's a warning here. because it's a common mistake, since the class P is considered polynomial. Some may think NP means not polynomial. No. The N here is not, doesn't mean not. Okay, it simply means non-deterministic. That is, the algorithm for this problem is non-deterministic. There is no deterministic algorithm for the problem. But somehow we can come up with solution in some way. All right, in non-deterministic way. But given that solution, it can now be verified whether the solution is correct or not in polynomial time. So this is where the P is coming. Non-deterministic, which is step 1 in generating the solution, but polynomial time to confirm whether a candidate solution is correct or not. That is the meaning of NP. So to give you again an example, Hamiltonian cycle is an example of NP, or example of a problem that belongs to NP class. So given a directed graph G, determine a simple cycle that contains each vertex in V. Okay, each vertex can only be visited only one time. So suppose we are given a sequence which we don't know how the sequence is generated. There is no deterministic algorithm to give us this sequence. Okay, we can easily determine whether the graph is Hamiltonian, the solution is correct or not. Okay, whether this sequence is from a Hamiltonian cycle or not. All you have to do is check that the vertices in the solution, they contain all the vertices in your graph. This is step number 1. Step number 2, make sure each 2 vertex, like V1 to V2, is a valid vertex in the graph. So clearly this will not run more than n times to check whether the solution is correct. Okay, so we are given this cycle. Okay, you can see from here, we go here, we go here, we go here, we go here. So it is a cycle. 2, does it contain all the vertices? Yes, it does. So clearly this is Hamiltonian, and verifying that it is Hamiltonian is really linear. First, just check that the vertices in the solution, are they corresponding to all the vertices in the graph? 2, the edges connecting each consecutive vertex, including the last one with the first one, are they valid edges? So if you can confirm these 2, then we have a Hamiltonian cycle. Okay, on the other hand, this is not a Hamiltonian cycle, because you can see here there is a repetition of an edge. Okay, so again, that's of course one of the things you should check here when checking for Hamiltonian, whether the solution is correct. There should be no repetition of the edge of the vertex. Okay, so here there's a repetition, and therefore this is not Hamiltonian. Remember, if there's a repetition of the vertex, we don't call it a cycle, we call it a circuit. Right. So this is an example of a problem that belongs to NP. In fact, it belongs to NP-complete, as we shall see later. Okay, now the next interesting question is whether the 2 classes we have seen so far, whether they are equal. Okay, is P equal to NP? Okay, one thing we can observe is that any problem in P is also in NP, because a problem in P can be solved in polynomial time, not just talking about verifying its solution. It can be solved in polynomial time. If it can be solved in polynomial time, definitely verifying its solution can also be done in polynomial time. Therefore, the class P obviously is a subset of the class NP. Okay, all problems that have polynomial solution can also be verified in polynomial time. The question is, what about the reverse? Can we say NP is also a subset of P? Okay, so here it says the big question, which is actually an open question for many years so far, is whether NP is a subset of P. Okay, in other words, if you can verify a candidate solution to a problem in polynomial time, does that mean there will be a polynomial time solution to it? So far, unfortunately, nobody has been able to prove either way. Nobody has been able to prove that yes, there is such a polynomial solution, and also nobody has been able to prove that there is not. So it remains an open question. Okay. If it is always easy to check a solution, should it also be easy to find a solution? This is what we are trying to say here. So far, nobody has been able to prove this question either way. However, most computer scientists believe that it is not possible, but they cannot prove it. Okay, they believe that NP is not a subset of P. Okay, so that, because if it is also a subset, then we have P equal to NP. So most computer scientists believe, this is just a belief, they are not able to prove it so far. This is why it is an open question. They believe that this is not the case, that NP is not a subset of P. That being able to verify a solution in polynomial time doesn't mean a polynomial time solution exists. So this is basically the class NP and its relationship to P. The next class is NP-Completeness. Okay, we're going to try to define it informally before we look at a formal solution. NP-complete problems are defined as the hardest problem in NP. So if this is your class of NP, then the hardest among them are what are called NP-complete problems. Okay, sometimes you will see them shortened as NPC. Some authors will abbreviate them as NPC, NP-complete. Okay. Most practical problems turn out to be either P or NP-complete. And we're going to mention a number of examples towards the end of this lecture. Now, to formally define NP-complete problems, we need to learn a term called reduction. Okay, so that's what we're going to study next before we give a formal definition. But informally, all it means is NP-complete problems are the hardest problem in the set NP, or in the class of NP problems. Okay. Okay, reduction. Reduction is a way of saying that one problem is easier than another. Or in other words, a problem cannot be harder than another problem. Okay. So this is how we define it. We say that a problem A is easier than problem B, and we write it as A is less than or equal to B. So here, less than or equal to means A is easier than B. If we can solve A using the algorithm that solves B, if we can do that, then we say A is easier than B. So let's explore this idea a little bit more. we are trying to solve problem A, but we already have a solution for another problem B. So what we do is we transform the input of A to be in the form of input of B, and then try to apply the algorithm for solving B to solve our converted input. Okay, so they say a picture is more than 1,000 words, so maybe this will explain it better. So here we have this box is telling us there's a black box that can solve problem B. Just give it an input like beta, and it will give you a yes or no answer. Okay, we know, of course, in all this classification we are talking about decision problems. The answer is always yes or no. So we have an algorithm that if we give it problem B, it can tell us yes or no as the answer. And now look at the bigger box. We are trying to solve problem A. We don't have an algorithm for solving A. However, if we convert the input of A, so alpha is the input for our problem A, we use some conversion function f to transform it to input that B can accept, okay, or the solution to B can accept, the algorithm of solving B. Now we pass that converted input and we get a yes. If we get a yes, then we say the solution to our problem A is also a yes. If we get a no from B, we say the solution to our problem A is also no. So if we are able to do this, then we say that we have reduced problem A to problem B. And we also say that A is easier than B. Alright, so this is the idea of reduction. Polynomial reduction. Let's now look at a special case of this reduction. Given two problems, A, B, we say that A is polynomially reducible to B, and we write it as this. So instead of just less than or equal, we attach P. So it means A is polynomially reducible to B if 1. There exists a function f that converts the input of A to the input of B in polynomial time. Okay, so our function is not any arbitrary function. It's a function that will transform the input of A into the input of B in polynomial time. And 2, A of I is yes if and only if B of f of I is equal to yes. In other words, if we take any input of A and transform it using our polynomial function to an input of B, okay, we shall get yes in A only if we will get yes in B. Okay, so I mean if we get no, this one will also give no. Yeah, so essentially it's the same as the definition of reduction that we saw earlier. The only addition here is the conversion from input of A to input of B is done in polynomial time. Okay, good. So with this idea, we can now define what is NP-completeness formally. A problem B is said to be NP-complete if 1. The problem belongs to NP. So the problem definitely is NP, meaning it can be verified in polynomial time. A solution to it, any candidate solution, can be verified in polynomial time. 2. A is polynomially reducible to B for all A in NP. Okay, please take note, our candidate problem is not A, it is B. So basically what we are saying here in the second condition is all problems in NP are polynomially reducible to our problem B. So you can see B is the harder one. All problems in NP are easier than B. Okay, A is easier than B for all A in NP. If that is the case, then the problem B is said to be NP complete. It's the hardest in NP. I hope this is clear. A problem B is NP complete if 1, it belongs to NP, so it is in the set NP, and 2, any problem you take in NP or all the problems in NP are polynomially reducible to that problem B. Okay, the common mistake is to think it is B that is less than a problem in NP. No. It is all the problems that are already confirmed to be in NP, they can be reduced to B. They are easier than B. So B is really very hard. If that is the case, then B is said to be NP complete. This is the idea. Okay. Now, this can also allow us to define the last class, which is NP hard. If B satisfies only property 2, we say that B is NP hard. So NP hard problems are not in the set. They don't belong to NP. Okay? And in addition, all problems in NP are easier than them. Then in that case, such kind of problem is called NP hard. I hope now the 4 classes are clear. Class number 1 are the easiest one. We can solve the deterministic algorithm to solve them in polynomial time. Okay, NP, there is no non-deterministic algorithm to solve them in polynomial time. However, if given a solution, we can verify the solution is correct in polynomial time. So these are called NP. NP complete are those problems that they can be verified in polynomial time, but they are also harder than any problem in NP. Okay? And the final group, NP hard, are those that are harder than any problem in NP, and they themselves are not NP. I hope the 4 classes are clear. Okay, no polynomial time algorithm has been discovered for an NP complete problem. Okay, so far no such algorithm has been found. Okay, also the reverse is true. No one has ever proven that no polynomial time algorithm can exist for any NP complete problem. So maybe you guys or some of you, some brilliant student in the future may come up with solution to NP complete problem. So that has not been proven either way. Yani, no polynomial algorithm has been found, and it has not been proved that one cannot be found. Okay, this is why the question of whether P is equal to NP is still open. We just don't know. I hope this is clear. Okay. Now, there is an implication property or 2 properties about implication of reduction which you should take note of. It says if A is polynomially reducible to B and B belongs to P, okay, then of course A belongs to P. You see, A is easier than B, and B is easy, it is belonging to P. Therefore, A must also be belonging to P. Another property, if A is polynomially reducible to B and A is not in P, then B cannot be in P. Okay, see, A is easier than B, but even though A is easier than B, it is still not in P. How about a problem B that is even harder? If A cannot be in P, then of course B cannot be in P. Okay, so these are obvious from the definition of reducibility. How do you prove that an algorithm runs in polynomial time? You can use reduction. First of all, you need to have a well-known algorithm that is proven to run in polynomial time. Okay, so we have a polynomial time algorithm for a particular problem B. Okay, so what you do is the following. We use a polynomial time reduction algorithm to transform A to B. Okay, so you take your problem A and transform it to that algorithm that you say has polynomial time. But your conversion algorithm has to be polynomial too. Okay, this is step number one. So convert the input of A to that of B in polynomial time. 2. Run a well-known polynomial time algorithm for B. So you will apply basically your input that you have transformed to this polynomial time algorithm. And finally, use the answer for B as the answer for A. Okay, so if you can do all these three, then you have successfully proven that problem A can be solved in polynomial time. You don't have to actually come up with an algorithm for problem A itself, provided you can convert its input to input of B in polynomial time and apply the solution of B, and the algorithm of B itself run in polynomial time, then definitely your original problem A can be solved in polynomial time. This is another way to do it, and this is what is done by computer science people for problems for which the algorithms are not yet known, but it can still be proven that they have a polynomial time solution. Now we have said earlier that for a problem to be NP complete, if you recall our definition, first it has to belong to NP, and 2, it has to be easier than all the problems that are NP. Now, do you have to take all the problems that are NP? There are thousands of them to show that a new problem is also NP complete? In practice, no. You don't actually have to do that. So to prove that a problem B is in NP, a randomly generated solution can be checked in polynomial time to determine if it represents a solution. Okay, so that is for NP. This is very easy. Now, how about it is NP complete? Okay, so show that one non-NP complete problem can be transformed to be in polynomial time. All right, you don't have to show all of them, just picking one problem that is known to be NP complete and showing that your problem, that NP complete problem is easier than your problem B. If you can do that with just one NP complete problem alone, then in practice that is good enough to show that your problem is indeed NP complete. Okay, so no need to check that all NP complete problems are reducible to B. Just one is enough. Okay, a final revisit to our P equal to NP. is shown by this theorem. If any NP-complete problem can be solved in polynomial time, then it is a proof that P is equal to NP. Okay, this is a theorem. We're not going to prove it in this lecture or in this course, but the proof is there. If you can prove one NP-complete problem, okay, to have a polynomial time solution, just one of them, then actually all of them will also have polynomial time solution. And that means the set NP will be a subset of P. We already know that P is a subset of NP. Okay, therefore combining the two, it will mean that P is equal to NP. Okay, this problem has been there for many years. So far, nobody has been able to prove even one NP-complete problem to have a polynomial algorithm for solving it. Nobody. Okay, so this theorem is saying if there is ever one person that come up with such a solution for only one NP-complete problem, if any one of them is proven to be P, then all of them will be P as well. And therefore the question P equal to NP will be answered once and for all. Hopefully one of you will be bright enough to solve this particular problem.